So today we're going to talk about humidity, evaporation, and boiling. A lot of this has to do with ideal gas law and the relationship between pressure, temperature, and volume, and kinetic energy and thermal energy. They're all connected. And so we started with this image of dewdrops on a banana leaf, and they form because the air temperature drops, and in the air there are molecules of water, and so once it drops below a dew point, the water molecules will go from being a vapor to a liquid, and they'll form. The rate at which these water molecules join together is greater than the rate in which they separate. So they're in an equilibrium, and then they shift towards liquid. And some of the water condenses to form little droplets. So, and when you can have droplets and condensation, and you know, and there's an impact of different things. So here we have an example in Figure A. Because the distribution of speeds and kinetic energies, in other words, not every water molecule is going to have the same energy. Some water molecules can break away from the vapor phase, even at temperatures below the ordinary boiling point. And so that's what you have over here. We have some molecules that have broken away from the water just because they have extra energy. All right. And then in in Figure B, if the container is sealed, evaporation will continue until there's enough vapor density for the condensation rate to equal the evaporation rate. This vapor density and the partial pressure it creates are the saturation values. These increase with temperature and are independent of the presence of other gases such as air. So these depend only on the vapor and pressure due to water. So here, there's really nothing keeping this water molecule from literally escaping out of the pot, but because we have a lid here, the water molecules will bounce off the container. That creates a little bit of pressure, but also you'll see condensation forming on those surfaces because the molecules kind of collide into the surface and they kind of lose a little bit of energy. Where in Figure A, because it's so open, you might have a little condensation right here where things are, they escape the vapor, and then through that process of escaping, they lose a little bit of energy and condense back down to liquid. And so those are the two things that we want to consider today. The relationship between pressure and temperature and the amount of saturation you can have. There's a table that has a bunch of these values and how they're calculated. This is in the online textbook. You could take a look at it. I will jot this down because I don't know why I didn't make this. So when water is boiling, this should be in here somewhere, so I'm just going to write it down. I keep hitting the wrong tool. Okay, so when the temperature is at 100 degrees Celsius, then the vapor pressure is 1.01 times 10 to the fifth. Oh, shoot, that's going to be a 10 to the fifth. And then our saturation density is going to be 598 grams per cubic meter. So that's how much water vapor you can expect. And there's a table that has all these different temperatures. And so that's pretty much it. So let's see how we use this information for this next question here. We're going to calculate the density using vapor pressure. So the table that I just showed you gives the vapor pressure for water at 20 degrees Celsius as 2.33 times 10 to the third Pascal. Use ideal gas law to calculate the density of the water vapor in grams per uh, meter cubed. That would create a partial pressure equal to this vapor pressure, and then compare the results. So the first thing that we're going to do is I gotta make some changes here. The temperature in Kelvin would just be this 20 degrees plus 273, and that gives me 293 degrees Kelvin. And then this, we'll use this later. And then the molar mass for water, remember the molar mass for water, oxygen is 18 and hydrogen. So let me write this down. So oxygen has a molar mass of 16, and then we're going to have 2 hydrogen. So then your total molar mass, or molecular mass, I'm sorry, molecular for H2O is equal to 18 grams per mole, right? So I'm trying to write stuff down, and I'm saying things. What I'm writing down is accurate, right? This is like if you look in the periodic table, and that'll give you the molar mass, and then we add that up. All right, so remember that our ideal gas law, and I'm going to try to write tiny here. Let me change the color. Remember that PV is equal to lowercase r, or lowercase n, times r times t, right? And so basically what we want to do for where n is our number of moles, if we solve this equation for n over v for the volume, that'll calculate the number of moles per cubic meter. So what I'm going to do is I want to make it look like n over v. So first I'm going to get stuff away from the n, so I'm going to divide this side by RT. And divide this by RT. And I get PVRT equals n. And then I'm going to multiply this by 1 over v, and then just divide this by a capital V. And so I get P divided by RT equals n number of particles or moles over V the volume, right? So that gives me my moles per cubic meter, right? So let me write that down. My unit for this will be moles per meter cubed. All right, so far so good. So now I'm going to plug those values in. I'm going to say n over V is equal to my pressure, right, which is 2.33 times 10 to the third pascals. All right, and then R is a constant, so that would be 8.31 joules per mole Kelvin. That's the unit for that, times my temperature, which is 293 degrees Kelvin. All right, so Kelvins cancel, joules, blah, 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 blah. If I plug that in the calculator, I end up with about 0.957 moles per meters cubed. Okay. And so remember, we're trying to compare the vapor density using the ideal gas law. What we want to do is calculate the density of water vapor that would create partial pressure in this vapor pressure. So there's a vapor pressure, and we want to calculate the water pressure. So we're not quite done yet. We need to convert this to find the density, right? Because that's really what they're asking us to do, is find the density of the water vapor. Okay, so remember that density, I gotta be careful how I write this. So density is a measurement which is the mass. Well, where can I write this over here? I'm going to put it over to the side. I'm starting to run out of room here. Density, which is like it's a funny shaped P. Looks like that. Well, I'll write it up here. We kind of do this. Density is equal to the mass of the object divided by the velocity. And so, not velocity, volume. Oh, it's been a long day. I did velocity questions earlier today. So that just means that I'm going to multiply. So to find rho here, I'm just going to multiply NV over times the molecular mass, right? So I have the molecular mass, which is in grams per mole, right? So divided by the volume, and then what happens is the moles cancels out. So let me write it out. Maybe it'll make more sense. This is 0.957 moles per meters cubed times the molar mass, which is 18 grams per 1 mole. And remember that our density is going to have to be this right here, grams per meters cubed. And I don't know, sometimes if I over explain this stuff, it's too much. But the moles cancel and I'm left with grams per meters cubed. Okay. You could think of this N over 1 over V, because you could think of this up here as the mass times 1 over V, where the molecular mass, the way that we've structured it, because it's 18 grams per mole, that's going to be the same as the mass over the number of particles. And then this is going to be the number of particles over the volume. So this is like N times 1 over V. And then this up here, the molecular mass, is like the mass over the number of particles. And so when you multiply the mass over the number of particles times N times 1 over the volume, these will cancel and I get a mass over the volume, which is the very definition of density. Okay, so that's how you get that. Oh, hey, let's plug in the numbers so we know what it actually is. So when we do all this math, when I multiply this number times this number, we're going to get 17.2 grams per meter cubed. And that's the final answer. So that's how you would calculate that. So it seems like a lot. So what I always like to do at the end is double check. So using the table, that gives us the vapor pressure for water at 20 degrees Celsius as 2.33 times 10 to the third Pascal. Use the ideal gas law to calculate the density of water vapor. In other words, how much water is there compared relative to the volume, right? Like how much mass of water do you have relative to a volume, grams per meters cubed. That will create partial pressure equal to the vapor pressure. Now this is important for calculating a lot of stuff. And then we're going to compare the saturation density compared to the given table. So what does that mean? Well, it means that our vapor density of 17.2 grams per meter cubed at 20 degrees Celsius creates a partial pressure of 2.33 times 10 to the third pascals, equal to the vapor pressure of water at that temperature. If the partial pressure is equal to the vapor pressure, then the liquid and vapor phases are in equilibrium, and relative humidity is 100%. Thus, there is no more than 17.2 grams of water vapor per cubic meter at 20 degrees Celsius. So this is the value, is the saturation vapor density at that temperature. This example illustrates how water vapor behaves like an ideal gas. The pressure and density are consistent with the ideal gas law, assuming that the density in the table is correct. So the saturation vapor densities listed in the table are the maximum amounts of water. So you can have less, obviously. And so what does that mean? Well, I'm going to move on to the next slide. It means that we define percent relative humidity as a ratio of the vapor density to the saturation vapor density, or percent relative humidity. So when they talk about humidity and it says a percentage, it's the vapor density versus the saturation density. So you're going to have some sort of density here, that's the vapor density, and then you're going to have another saturation density. This is the maximum amount that you can have. Okay. Now, when they equal each other, and so this will, when you do the math on this, this will be a decimal, and then we just multiply it by 100 to get whatever the percentage is. Okay. So when they say we're at 80% humidity, what they're saying is that our vapor density is 80% of the saturation vapor density. So usually when you see humidity of 100%, it's the state of equilibrium, and it's probably going to rain soon, right? So anyways, I hope everybody's got that written down, but it's just the vapor density, what the actual vapor density is over the saturation, how much can be held in that medium, or air, or fluid. Technically it's a fluid. Air is technically a fluid, water is technically a fluid. All right, so let's figure out the humidity and dew point now that we've learned so much about this stuff. So it says calculate the percent relativity on a day where the temperature is 25 degrees Celsius and the air contains 9, I'm going to start highlighting some things here, 9.4 grams of water vapor per cubic meter. So that's part A. B is, at what temperature will the air reach 100% relative to the humidity, the saturation density. And this temperature is the dew point, so that's important. And then, so the dew point is where it's fully saturated, the air can't hold any more water, and then it starts to form dew. Okay. What is the humidity when the temperature is 25 degrees Celsius and the dew point is negative 10 degrees Celsius? So how do we do this? Well, we've got to remember from the previous slide that your percentage of humidity is equal to the vapor density. Vapor density, I'm just going to spell it out, over the saturation density. Okay, or I'm going to say density rho v over rho s, where lowercase v is vapor. Oh, I forgot to do the s though. This is an s. I'm going to have to start using PowerPoint. All right, so times 100. Okay, so based on our table, if I go back and I look in our table, our vapor density they give to us, right, they said that the vapor density at this temperature, the air contains 9 points. So that would be 9.4 grams per meters cubed. And then if you look in the table at 25 degrees Celsius, it's actually 23 grams. That's the saturation. So what does that mean? Okay, for every cubic meter, the top number, 9.4, means that for every cubic meter of air, it can hold 9.4 grams of water. But at 25 degrees Celsius, the maximum saturation, the maximum amount of water that the air in a cubic meter can hold is 23 grams. So this is how you figure out your percentage of humidity. Well, if I do the math on this, I end up with 40.9%. Okay? All right. So that is part A. Okay. So now for part B, really what I want, if I want 100%, so part B says, when will this reach 100%? Well, it reaches 100% when my density, my vapor density is equal to my vapor saturation. So I go back to the table. And I don't have the whole table in the notes. I wish I would have, but I'm going to go all the way back until I find 9.4 or somewhere close to 9.4 in here, and that there'll be a corresponding temperature to that. So let me see if I can find this in the. I have the textbook right here. It's going to be tough. Oh, they rigged the problem. So if I go back here, let me do this. Well, I can't, I showed it on the screen, but basically at 10 degrees Celsius, if you look in the textbook, that will give you the maximum saturation density of 9.4. Okay. So for part B, the answer, and you just look this up, because when that happens, what I end up with is 9.4 over 9.4. And then that equals 100%. Okay. Let me see what so that's part B. Let me just double check and make sure. Yeah. So yeah, in that case it's 10%. So for part A, well, we'll recap. This is part A. Part B is 10 degrees Celsius. And then for part C, it says, what is the humidity when the temperature is 25 degrees Celsius and the dew point is -10? All right, so again, we have to go back, right? So it's the same formula. We're going to have the percentage of relativity, right? And so that's going to be the vapor density over the vapor saturation. All right. And so if I go way back and I look at -10, let me just double check. So the dew point is given to be -10 degrees Celsius. We see the vapor density. If I go back in the chart, I wish I could show the screen here because I have it. Well, maybe I could slide it over. We'll see. Okay, well, let me slide it over. Yeah, here. So this is what I did is I went back into the textbook. This is where I got the 9.4 for the last problem, but they say the dew point is -10. So this is my maximum saturation right here, which is 2.6. So we're going to assume that at -10, the most water that can be held in the air is 2.6 grams per cubic meter. Okay, so let me slide that back over here. So then that would mean I'm going to have 2.6 over the 23, right? So the most amount of relative humidity that I could have is I'm going to have this 2.36 grams, because that's all the water that can be held at -10 degrees. And then over here I've got 9.4, or not 9.4, this is going to be the 23. Because that's the maximum saturation I can have at 25 degrees Celsius. Okay? So then what is that relativity? About 10.3%. Okay? So to recap, I'll write this in a different color. My answer is 40.9%. For part B, my answer is 10 degrees Celsius. And then for part C, based on the dew point at -10, I've got 10.3%. Okay? I'll leave that up there so you can kind of digest it. All right, let's move on to the next slide. So I'm going to boil some water. So what they're saying here is that there's a little air bubble in figure A where it starts out saturated with the water vapor at 20 degrees Celsius. As the temperature rises, the water vapor enters the bubble because the vapor pressure increases. The bubble expands and keeps the pressure at 1 atmosphere. At 100 degrees Celsius, the water vapor enters the bubble and continuously, because the water vapor's pressure exceeds the partial pressure in the bubble, at which it will become less than 1 atmosphere and the bubble grows and rises to the surface. And so there's actually air trapped in the water. And this is why when you first start to see water boil, some of the air can actually come out of the water, and it's kind of a neat thing. And then and it's really vapor, right? It's not water. There's some air in there, but the reality is some of that water is becoming vapor. And because let me write it like this. So this is vapor. This little dot here is vapor. Okay, so let's label this. There are air bubbles, but this little dot is just vapor. Why? Because as you add heat, some of that water has extra kinetic energy, but the pressure from the inside of this coming out is about 1 atmosphere. And the pressure that's pushing down is also 1 atmosphere. And the pressure right here is also 1 atmosphere. So this water vapor keeps causing this to expand, and water vapor leaves the liquid state. So this is liquid, right? This is the liquid, and this is more vapor. And so at this point here, what's going on is that the vapor, right, can actually make the pressure inside here. In other words, this pressure is different than the pressure pushing it down. Okay, So the bubble expands and keeps the pressure at 1 atmosphere. So inside this bubble, it's 1 atmosphere. Inside this bubble, it's 1 atmosphere. But at 100 degrees, the vapor bubble continuously expands because the water vapor pressure exceeds its partial pressure in the bubble, which must be less than 1 atmosphere. So this is like less than, did I write that right? Yeah, 1 atmosphere. And so the object that's less dense is going to float to the top, where over here it's going to be that. Okay? And that's it. So the bubble grows and rises to the surface. And that's it for the notes today.